Uh, yeah, Matt from University of Notre Dame is gonna talk about the second test suite, which is about approximation of problems with parameter-dependent discontinuities in steady aerodynamics.
All right, thank you very much. So this test case is organized by myself, Patrick Lonigan, Masa today, and Masayuki Yano. And the motivation for the test suite is unsteady aerodynamics. Once we go to the next slide, is steady aerodynamic flows. And there's obviously going to be many others, but this is kind of the cases that we're going to keep coming back to that are going to be pretty broad interest. And the idea here is that in aerospace, we want to make predictions of lift, drag, heat transfer, many other different quantities of interest over a range of operating conditions under varying geometries, because we want to do things like optimization, we want to sweep parameters, we want to do uncertainty quantification, all of the standard things that the ROM community is interested in. We want to do that in steady aerodynamics, and we face this problem is that even though these problems are steady, they're very hard to converge. They require really fine grids. You got shocks that move around, so the kind of the most appropriate grid for a given test case changes. So kind of standard practice is to either use some very fancy like adaptive mesh refinement, or just predetermine where your shock and moving feature is going to be and refine the hell out of that whole area. So it just leads to challenging large-scale problems, and that becomes an issue, of course, when we want to start to vary parameters and solve that many parameter configurations. So let's go to the next slide. Master, can we change slides?
Yeah, sorry, there's a delay. Sorry about that. Yeah.
Oh yeah, no, it's fine. And then so the way that we're going to kind of just visually describe the problem and the issues that model reduction faces is that we're going to do a simple 1D kind of very contrived problem where we have a parameter dependent shock. So we're going to take two snapshots. So we're going to have there's, you can see two just kind of snapshots of this parameterized shock here. And the idea is that now we would like to use that information to hopefully predict something right in the middle. And the idea is that if we do some sort of TOD or any kind of a linear approximation that's going to take linear combinations of those snapshots, really the best that you can do is going to be some sort of a staircase approximation to the shock, which is not going to get you very accurate quantities of interest. You're going to be lucky if you're going to even be able to stably converge these kind of things, because these kind of oscillations can cause CFD codes to all kinds of havoc. They can crash and all sorts of other issues arise from solutions like this. And that's just, I mean, that's apart from the fact that these are obviously horribly inaccurate solutions, and that's not really acceptable for our purposes. So that's the point of this test suite, is to be able to figure out which model reduction methods are capable of overcoming these kinds of things. So on the next slide here, we'll just talk about one idea that's been around in literature. I've worked on this area, Tomas has worked on it, and others are getting into this now. Patrick and Masa are both doing things in this direction these days. So the idea is actually very simple, is that, of course, if I have a single mode, which you can see up here in this top figure, and I wanted to use a linear basis, all I can really do is scale it, right? If I had more, I could do linear combinations, but you're kind of beholden to wherever those shocks work. But now if I were to actually take this single basis function, and I were to compose it with a mapping G, and this G here, you can see I just made some very contrived thing, and it depends on this parameter tau. As you start to change tau, you start to kind of deform the underlying domain. So in some sense, the distance between points in the domain, and that causes that shock to actually move around. Now, of course, that the dependence on this basis function now, it depends on tau in some nonlinear way that comes from this composition of functions, but it's it really does kind of solve this kind of fundamental issue of I have a snapshot with a shock in one spot, and now I need that shock in another spot. So that's the idea that we're looking at, and this idea readily extends to 2D and 3D, although it's a little more complicated in those areas. So then the kind of follow-up idea behind this is that if we can now, how do we actually generate data that we can leverage this idea? There's this idea of a snapshot alignment or registration, where if on the left curve, on the left side, we have kind of a set of information that deals with non-aligned snapshots. So you just see this in this top left figure, this little bump that's moving and kind of sharpening into a shock. And then on the second row, you see these the basis functions that you would get from just doing standard POD, and then the decay of the singular energy on the bottom left. And you can see it decays very, very slowly. And those vertical lines are what you would need to get 10 to the minus 3, 10 to the minus 6, and 10 to the minus 9 truncation energy. And if you want to get 10 to the minus 9, you really have to basically include everything. Now, on the other hand, if we were to actually magically align or register these snapshots relative to each other, then the modes look very different. Really, the first mode kind of takes care of the shock, and then the future modes kind of start to resolve things on either side of it. And even in some sense remove the convection dominated feature, and you now get these kind of rapidly decaying singular values, and that's what you see on this kind of bottom right. You get 10 to the minus 9 now, which is that farthest dashed blue curve on the right. It requires far, far fewer modes. And that's that's just one idea of many on how to kind of overcome this irreducibility of these convection dominated problems. So we're going to let's just jump into some of the actual test cases that we're going to consider. And the first one is the just very standard inviscid flow through a nozzle. So it's nice because it's the Euler equations, but it's also a relatively low barrier to entry because it's not some complicated 3D thing. It's 1D, right? So it's the hope is that we can assess some of these new methods on a standard kind of test problem, and that test problem is not going to take every 1 month to code up, right? So that's the idea. And it's a very simple, steady 1D problem. You can see the governing equations here. And the parameter is coming into the area A here. That's the area of the nozzle. And you can see just a couple of configurations of the nozzle that we have plotted on the bottom here. So let's move on to the next. And if we apply that idea that we saw a few slides ago to this problem, if you can see on the top, as you start to change that nozzle throat area A there, you get the shock that's going to move around. And this is kind of an actual example relative to my cartoon on the first slide. But you can see if you were to try to predict anywhere in between those shocks, all you could do is staircase approximate it, right? And of course, the more that you get, the more snapshots you take, the better that approximation is going to ultimately be. But it's never going to get away from staircasing. And also, one of the hopes of this workshop is not to just assess online accuracy and performance of ROMs, but to also take into account how much training is required too, because that's some metric of success too. If you can get pretty accurate predictions, but with not a ton of training. So now, if we apply the whole map snapshot idea, you can see that those discontinuities in the bottom are all aligned, and really the different parameters are just kind of tweaking the solution on either side. That's much more reducible than the original snapshots are. So then if we look now at kind of the singular decay, we can look at these black curves, which are with non-alignment, and the other one, which is with alignment or this registration. And you can see there's a much more rapid decay of the singular values, which is on the left, and a much more rapid decay of the energy. So, and the idea is here, what we did is we just sampled a bunch of points, and we took like 100 different values of mu, and we collected data for it. We just looked at how the singular values decay and the aligned versus non-aligned basis, that's the left. We looked at how the error of the online distorted model decays as you start to grow that basis, right? So there's not really any prediction here. It's just on a growing basis, how does these errors decay? Okay. And just like I said, quick example of that. So that's our first test case. So we're going to go through the test case, and at the end we'll just talk about things like error metrics and ways to assess. So we're just going to introduce the test cases first. So the next one is it's very similar to the one before in the sense that it's Euler equations, but now we're going from 1D to 2D. It's also a relatively simple problem. It does have a non-trivial geometry. I mean, it's curved. It's not, but you can create your own grids for this. It's not like you have to have super complicated mesh generators. And the idea is that it's just some flow that's coming over this bump. It speeds up, and you get a transonic shock that's going to be attached to this curved boundary. We're going to vary the Mach number between 0.58 to 0.78. It's going to vary the shock's position and strength. And then we have expression for the bump there, and this is just going to be the compressible air for ideal gases as well. So if we look at a few snapshots, that's also generated for this one. You can see that in the when you take the bump height and the Mach number to be, you can see what it is in A here. You get the configuration on the left that doesn't really have a shock, and as you start to change those things, the shock strengthens and kind of moves backward on the bump. So the challenge here is that after you get beyond Mach number 0.65, you're going to actually get these shocks to form, and you're going to have a lot more sensitivity to the actual shape of this bump. But like so, the shock, we're going to consider parameter variations where the shock quality doesn't change. The Mach number gets high enough, and all of a sudden, your shock structure is going to be a lot different, and that would tax methods in other ways that are relevant. But for now, just to try to keep the test case relatively simple, we're going to focus on parameters that don't cause shock topology changes. So the next one is the supersonic flow over just some blunt bodies, the cylinder in this case. And the goal here is to really assess how these methods work for bow shocks and supersonic flows. Again, the complexity increase from the former problem to the bump to this one is relatively low also, in the sense that there's it's the same governing equations, it's also still in 2D. And now I guess the big difference is that the domain is a little bit more complicated, but it's still just going to be flow around a circle. So, pretty much any unstructured mesh generator would work for that. You can also create your own grids kind of by hand if you don't make the boxes, be a perfect intersection of a circle and a rectangle. But the idea here is we're going to sweep the Mach number between 2 and 4. As that Mach number changes, the bow shock's going to get stronger, and it's going to move toward the cylinder. So again, it suffers from this problem that you're going to have snapshots with shocks in different locations, and you're going to have to figure out ways to reduce that. So now we'll talk a little bit about metrics, and this is just going to be kind of some of the ones that we've come up with so far. Other co-organizers of these test cases will jump in with comments at the end, and also happy to have a kind of discussion on what's relevant. But we really kind of thought there were going to be 3 really important things that assess whether or not a ROM in this setting is going to be good in some sense, right? Obviously, there's accuracy, and we want to talk about accuracy as a function of not only the reduced order model size. I would say that's fairly common, but also accuracy as a function of how many snapshots you need, right? Because you might be in very different regimes where in one setting you really care about having as small and fast a ROM as possible, but in another setting their snapshots are insanely expensive to generate, like in some maybe hypersonic applications, and you really can't afford many snapshots. So we really want to kind of know where that Pareto front is in some sense of accuracy relative to not just ROM size, but also snapshots. And things that we consider doing are just like LP norms for problems that have known solutions. There's things like violation of conserved quantities, like for the inviscid flows that we know that the global enthalpy should be conserved. So that's an actual, very concrete and rigorous kind of error metric that can be used. And then also output errors in the other cases that as they get a little bit more complicated in the future. But even for the ones that we've considered here, of course, we care about lift, drag, temperature on surface, things like that. So, and these things for participants are always, once you've done the simulations, you just have to output some of these quantities, and that's a fairly low burden as well. So that's, and the more information that we have, the more things that the test case leaders can post-process and plot and see how the trends are for different methods. Of course, related to this conversation, we also want to consider offline costs, right? That's related to this end snap. But of course, the offline cost for different methods is not purely end snap. Or in snapshot, there could also be, however expensive the ROM is to construct, right? Maybe there's a POD, the proper orthogonal decomposition in there, and that's a non-trivial amount of cost because you have to do some large scale SVD. There might be some neural network training, some hyper reduction where you have to solve some linear programs or some non-linearly squares problems. Right, so that's important kind of relevant information to include. And the motivation for including this is that a lot of times in these aerodynamic design applications, you just have turnaround times and computational budgets where you just simply can't have an insane amount of offline costs. And if you do, it makes the ROMs almost not useful, right? So that's one regime where we're going to kind of know where some of these methods sit. And then, of course, the standard one in the ROM community is how fast is your ROM once all the training is done, right? So And that's something we're of course interested in as well. So just to summarize, and then I'll stop talking, give other test case leads and anyone else that wants to jump in, is that, of course, the motivation for this is that we want to do efficient model reduction for transonic, supersonic aerodynamic flows. And there are other, application areas out there that do have parameterized discontinuities that would be interested in ROMs that can solve the challenges in this field as well. And the fundamental challenge, as we talked about, is this parameter-dependent shocks really slow inlet decays, and that just causes fits for the standard model reduction technology. So really our goal here is to develop, assess, and compare some various nonlinear model reduction techniques. And so we can just kind of come together as a community and see how these methods are doing. Just to remind you, the 3 test cases are the transonic quasi 1D nozzle, transonic Gaussian bump, and the supersonic cylinder. And as just discussed, the important assessment metrics are accuracy, offline training costs, and online training costs. And we are, of course, as get closer to an actual workshop on this, we'll have more details on the actual ways that those things can be reported. But we also want to leave it somewhat flexible because we understand that the array of methods that exist out there, there's many, and there are very different flavors. So we want to make sure that we can have participation from people that are have a method that doesn't necessarily fit so cleanly into a very tight box that we define on how to quantify offline costs. So that's something that we've been discussing a lot, and we're open to input from people. So with that, I'm done.
Thank you very much, Matt, for the presentation. And I think there's time for a few questions so that we stick with the program. Are there any questions from the audience?
Yeah, Matt, are you going to provide just the data or also the code to people who are interested?
I think the idea was to, there's not really any necessarily data for this. The problems are kind of well defined. So the idea was, I don't think that we would necessarily provide code unless there would be participants that would find that useful, and they would be willing to participate if they had code. But if they don't have code, then they would not. Then we would certainly do it. I'm just not sure if there would be anyone that would fall into that then or not. So I don't think it's something that we're potentially open to. I'm not sure if we would do it without, I guess, motivation to do it. Just because, I was thinking from a practical standpoint is that a lot of the nonlinear model reduction techniques tend to be intrusive. That's not obviously all of them, but a lot of them do be are. So I'm not sure how many people would benefit from a code, but if there would be some, then I'd be happy to hear that.
Yeah, I think the point about coding is quite interesting. I think we have to discuss about that. Perhaps we can leave it to the discussion at the end. I completely agree with Matt that for these test cases, perhaps, in general, I think it's quite tough because everybody has his own code and he sticks with it. But perhaps for these test cases is somehow more doable, at least for the first one, I guess. But yeah, anyway, I don't know what other people think about that.
I would say for the first and second, potentially we could provide code. The third one's going to be pretty tough.
Yeah, I guess.
Because a lot of these things too are somewhat are dependent on how what kind of method you want to reduce, right? Do you want to use your method to work well with any kind of a approach, like any kind of a finite difference or finite volume or finite element approach? Does it assume one or the other? So those things are kind of make it challenging to provide these things.
I think if you want to test the whole procedure, starting from Florida model solve all the way down to actually having a hyper-reduced ROM model, I think it's hard to kind of provide bits and pieces. But I guess if someone's only interested in creating the map, for example, right? I could see a scenario where we provide mesh sheet on set of snapshots, for example, and just work on that, reducing the I guess this, yeah, just tackling that end width problem without worrying about other aspects of it, right? Like, for example, things like stability. That is a possibility, but I guess it depends on who might be interested in looking at this case. Yeah.
Yeah, I kind of agree with what Masayano just said. I mean that in the spirit of what Matt was saying before, also in a sense, if we provide a data set and then we say, look, just do the best you can do with this data set, it will put a common basis for everybody. And on one hand, you can focus on the reduction issue, or you can start from there and kind of use the database as a, let's say, tool to have a non-intrusive lower model, or have a kind of Galerkin lower model, which is kind of a priori, like for example, Nan explained before. So it gives a little bit of freedom on what you can do, still with the reference, which would be the data set.
Yeah, no, good point. Okay,